So we will start with the first lecture. Group theory is a subject which deals with groups which are set of transformations with some invariance properties. So essentially transformations which will leave some physical process invariant. In physics generally we describe a system by specifying its Hamiltonian. So if you make a transformation which does not change the Hamiltonian, we say that this particular system has got an invariance under such a transformation. So Hamiltonian will remain same. The transformation may be some kind of a rotation or a reflection, or it can be a kind of a phase change. So whatever transformation that you make, if the Hamiltonian does not change, then we say that the system has got such an invariance. You make a rotation or you make a phase change, local phase changes such are called gauge transformations. So you have a series of such transformations that you can make and put them all together as a set. Transformation 1, transformation 2, 3, etc. All those set of transformations will actually form a group. So that is called a symmetry group. Okay. So let us look at these things a little more carefully and in detail. So let me start with the definition of a group. A set G, and which I will denote it as G comma circle, is called a group if and only if the following axioms are satisfied. Is the font size okay? Lata teacher, can you read? Readable to the end? Okay. What are the axioms? First axiom is closure. So G should be closed under this binary operation O. What does it? It means for any two elements Gi comma Gj belonging to this G, Gi composed with the binary composition is that is a rule by which we can compose two elements of the group. So this result of this composition should also be in G. What does it mean? It means you take any two elements of the group, you compose them, then you cannot generate an element which is outside G. Every element, result of the composition of every two elements will belong to the same set. So it is closed, you cannot go out of the group. That is the closure property. Second property is called associative property. Simply call it as associativity. What is the meaning of associativity? For any triplet of elements, for any Gi comma Gj comma Gk in G, Gi composed of A, the result of composition of Gi Gj composed with Gk. That means the order in which you compose them is not important. This is called associativity. Third property, that there should exist an element E in G such that our Gi composed with E, and this should be true for all Gi in G. Such an identity element should exist in the group. Fourth axiom is existence of inverse to each element, which means for all Gi, a G in G such that Gi composed with Gi, this is equal to identity. This is for every element there should exist an inverse. So if any set with a binary composition is satisfying these 4 axioms, then we will call that a group. So this is the definition of a group. In addition, if for any Gi comma Gj belonging to G, Gi Gj composed with Gi, then the group is called an abelian group. So if you have up to 1 to 4, it is group. If you have this also, it's an abelian group. Yeah.
So these are almost like linear vectors.
Yes. So we have discussed this. We have defined this in the linear vector space. So if I have to give an example, any set of vectors, if you define V as a set of vectors, and this, so this G I will call it as V, and this binary composition I will call it as vector addition. Now if you consider V plus, that is set of vectors with vector addition, is always an abelian group. All these axioms will be satisfied for this. So when we defined vector space, we first defined these things with vector addition, and if you can recall, I think I wrote there that V plus is an abelian group. Okay, so this is the example I am giving because we already studied it in the linear algebra course. So V plus is an abelian group. So V plus is an abelian group is necessary for V to be a vector space, but it's not sufficient, because in vector space, in addition to set of vectors, you should also have a set of scalars, and there is another operation called scalar multiplication. So a vector space together with this vector addition and another field of scalars and scalar multiplication, it should satisfy a few more axioms with the scalar multiplication, like it should be closed under scalar multiplication, and then there should be a distributive property. If that all satisfies, then it will become a vector space. But for a set of vectors to become a vector space with respect to vector addition, it should be an abelian group. Okay, so these are the axioms that require to be satisfied for some algebraic structure. We call this an algebraic structure. G with a binary operation is an algebraic structure. For this structure to become a group, it needs to satisfy all this. Okay. Now supposing if some structure is satisfying only these 2 properties, okay, then such a structure is called a semi-group. If it is satisfying only 1 and 2, it is called a semi-group. But if it is satisfying only 1, 2 and 3, then that is called a monoid. These are just names for they exist, so I am writing. And if it satisfies 1, 2, 3 and 4 of a group. Okay. Now let us ask a question that suppose if I have a set with only one element, a singleton set, under what condition it becomes a group? That should be identity. Now if that's an identity element, you can verify that all the axioms will be satisfied. What is the inverse of an identity? Same, the same element, because E times E will be E. So if you ask this question, if, let us call that as, so this as example 1, So let's call example 2 as a singleton set A is equal to identity. Suppose if we have a set A comma, if I have two elements, when will this be a group? One of them should be identity. So let's say A is identity. Then B need not be identity, but what is B times A, B times E? B composed with E is B only, correct? E composed with B is B only. B composed with B, what should it be? It should be identity. B composed with B will not be B, right? B composed with B should be identity. So that is the A is identity and B composed B is identity. Under these conditions, it will become a group. In this process, in this sentence, when I am writing if and only if, what does it mean? Both forward and backward, both necessary and sufficient. So this is a unique condition. There is no other condition under which this becomes a group. This is the only condition. And we can go on asking these questions, 3 element, 4 element, etc. Okay? So let us reserve some of those exercises for the tutorial. We will ask a question to determine conditions under which a set of elements become a group. Okay? It turns out that and ABC equal to E. We can examine these things in the tutorial. So you can actually write down. Okay, so let me just introduce another concept which will become clear to understand this. Group multiplication table.